Okay, welcome to another video. This time we'll be solving AP Calculus BC test from 2014, number 1. This is a calculator problem. It's actually the first of these videos which requires a calculator that I've done. So I'm hoping to be able to introduce some side stuff where I can show you how to use your calculator a little bit. So what's the question? This is a very applied question we've got going on right now. So grass clippings are being placed into a bin where they decompose over time, sort of like mulch. They become mulch over time. We've got a function that helps us to model the amount of grass that's left in the bin after a certain amount of days. So this function is a function of time, and it tells us the amount of grass that's in the bin at any moment of time we could be interested in. T is our variable here, and it's measured in days. The name of this function is A, which is kind of like the amount of grass, and that's measured in pounds. Now, I already know this is a calculator problem because of the weirdness. We've got a bunch of decimals here to 3 decimal places and everything, so for sure this is going to be a calculator problem. Now, I like to get my bearings on these problems because I find these applied problems can be quite difficult for me. I'm just not sort of an applied person, so it's helpful for me to get my bearings and think about what's happening here. So what I went ahead and did is I put this function into my calculator. Of course, I'd use the variable x in my calculator, but that's no big deal. And what I like to do now is just kind of play around a little bit. This isn't necessary, but it helps me to understand what's going on. So for example, what happens when I plug in 0 into this function? What do I get? Now, I don't even need my calculator for that. A of 0 is 6.687 times 0.931 to the 0 power. This, of course, is just 1. This, of course, is just 1. And so we have 6.687 pounds. So what does this represent? This tells me that initially, on the day that I start counting, the initial amount of grass in my bin is 6.687 pounds. So this makes me wonder, I wonder how much there is after 1 day. Now, if this works out properly, this should be less than 6.687 because we're losing grass clippings as time goes on. So let's see if that's correct. We should realize that that has to be correct because notice we're multiplying here by a number that's smaller than 1. In fact, this is an exponential function that we're looking at here. Very common function to look at in calculus. And you can see that the rate of growth of this function is a number that's less than 1. In other words, the amount is in fact decreasing. So I don't know, I'm going to go ahead and check this out. And there's a little trick for doing this that I'll show you how to do. Since y1 is the name of my function, I put it into my calculator as y1. I can simply ask the calculator to tell me what is y1 of 1. And the answer is 6.266 approximately. 6.266 pounds. So note that I have, in fact, after 1 day, lost a lot of clipping. Not a lot of clippings, actually. It looks like 0.4 of a pound, a little bit less than a half a pound of clippings have disappeared in just 1 day. Just for fun, let's go ahead and figure out what's happening on the 30th day. I wonder how much there is on the 30th day. So 6.687 times 0.931 to the 30th power. And you can see, when you raise 0.931 to the 30th power, it's going to get quite small. That by 6.68. However, I'm simply going to ask the calculator for y1 of 30, please, and see what it says. And it tells me that there's 0.949 pounds left. So even after 30 days, we still almost have a pound of this grass left in there. Okay, so this is just me getting my bearings. This is telling me what's going on in each one of these days. Okay, so what does part A ask us to do? Part A asks us for the average rate of change of A, the average rate of change of A over the 30 days. And it wants us to give the units and everything for what this ends up being measured in. So that's what it's asking for, the average rate of change of A. So if you think about it, what's actually happening here is we've got something like this. I'm using a very rough graph here, but we know that A of 0, I believe we figured out, is something like 6.687 pounds. And here's time. And as time goes on, we're losing the amount of grass that's in there. This is a decreasing exponential function. We figured out stuff that, like, here's day 30, and on day 30 we had like 0.9 something left, pounds of grass clippings left. So what is this asking us for? It's asking us for the average rate of change of this function. So what it wants us to compute is the slope of the secant line. I missed there. The slope of that line. That's what it wants. The slope of that secant line. Well, this is very easy to calculate. Change in y over change in x. Very simple. So this is simply a of 30 minus a of 0 over 30 minus 0. So that's what it's asking us for. And like I said, we can calculate this really simply. I already asked for a of 30 minus a of 0. And then I divide that by 30. And we end up with negative 0.1912, negative 0.191, go to 3 decimal places. Now, what unit is this in? Very important in these applied problems that you give the appropriate unit. So what is this? This is a rate of change. It's the rate of change of grass clippings, which is measured in pounds over the time per day. So this is the average rate of change. It says that we are losing. The reason it's negative is because we're losing grass clippings. So on average, we lose about 0.191 pounds of grass clipping a day to decomposition. Of course, this is not a linear function. Actually, what's likely happening is that first we're losing it at a very fast rate, relatively, like we saw that on the first day we lost almost half of a pound. But it's leveling off as time goes on. Probably on the 29th to the 30th day, we lost hardly any grass clippings, but we still did lose some. Okay, so here we are into part B of this problem. Part B is actually really, really simple. Part B asks us to compute a prime of 15 and interpret what this means in the context of this problem. Like, presumably this has some meaning. We're talking about grass and bins and things like that. So what does this end up meaning? So that's what it's asking us to do. This is a straightforward derivative problem. I'm going to show you how to do this very, very quickly and simply with your calculator, also on the video here. But ultimately, we're being asked to take a derivative of an exponential function. For fun, I'll show you what this is very quickly. What a prime of t is. A prime of t in general is going to be, since this is an exponential function, it's 6.687 times 0.931 to the t times the natural log of 0.931. So ultimately, what you're going to do is plug 15 into this, but actually it's very much easier than that. And it turns out that a prime of 15 can be calculated with your calculator, again, using the fact that you've already put y1 in your calculator as the function. You can then find the derivative of this function with respect to x very easily, and then plug in 15. And the answer you'll end up getting is negative 0.164. Again, it makes sense that this is negative because this is the rate of change of the amount of grass clippings in the bin on day 15. So they also want you to interpret this. This is measured in pounds per day. It's the instantaneous rate of change. And what it tells us is that basically on the 15th day, you are losing about 0.164 pounds of grass clippings to decomposition. And you should probably write that sentence. On the 15th day, we lose approximately 0.164. Lose, that's what the negative sign does for us, approximately 0.164 pounds of grass clippings. Okay, so here we have it. We're finally on part C of this question. Part C is a pretty difficult one. Part C asks kind of a weird question. It says, find the moment in time over the first 30 days here when the amount of grass clippings in the bin is equal to the average amount of grass clippings that are in the bin over those 30 days. Okay, so that's what it is asking. Find, part C, find T so that A of T equals the average value of A of T over the first 30 days. Very weird question, but a question that also makes a lot of sense, right? The amount of grass clippings in the bin is changing over time. It starts out with 6.687, and I think we saw it ended on day 30 with like 0.9 something of a pound. So there are all these different amounts of grass clippings in the bin at all of these different days. But I can ask you the question like, but okay, but how many pounds of grass clippings are in the bin on average over those days? So this has something to do with what we call the average value of a function. So generally, the way we define the average value of a function is with the use of a definite integral. This should also make sense because a definite integral is a sum. And if you think about the way you calculate averages, the average grade in the class, for example, the way I would compute the average grade in the class is I would add up all of the individual grades, and then I would divide by the total number of grades that I have. I kind of want to do something similar here. I want to add up all of the different amounts of grass clippings that I have in the bin over these 30 days. Of course, there are infinitely many different amounts because we start off at 6.687 and we hit all of the different values in between there. And then I want to divide by the total number of times that I looked at how much grass clippings there were, which again is like infinite. So here's how we end up dividing it. The average value, the average amount of grass clippings is, I might call it like, I think we called it like A average. It's a single number. It's a Y value or an A value in this case. It's an amount. And it equals the integral from 0 to 30 of A of T dt. So I'm kind of adding up all of the time, adding up all of the amounts of grass clippings I have, and then I divide by 30 minus 0. I divide by the length of the interval that I'm adding this up on. So what I need to do is compute this number. This is a definite integral, which is a number, divided by 30, which is a number. And then I need to set A of T equal to this. And I need to solve that. I need to solve when does A of T equal this number. So this is going to be a pretty serious calculator problem. I'm going to actually ask the calculator to compute this integral for me. It's going to be a Y value. I'm then going to graph that Y value along with A of T, which you might remember I put in as Y1. And then I'm going to find out where they intersect. This is just going to be a horizontal line where the Y value is. So that is the plan for that. Okay, so now I've got my calculator. I'm going to try to do this. I'm going to ask the calculator to compute the definite integral from 0 to 30. The function I want to integrate is Y1. And then I want to make sure that I divide that by 30. So I don't need to know this value, but it turns out that this is approximately equal to 2.939 pounds. On average, over the 30 days, the bin has 2.939 pounds in it. Okay, so now what I want to do is I'm going to take that value and I'm going to graph it. So I'm going to put this into Y1 or Y2. Okay. So now one of the things that I think is very important when you're trying to do things, a lot of students just go ahead and hit graph and they do it from there, but I always love to mess with my window. So the first thing I realize is that the role of t is being played by x here. So we're talking about x values, and we're really only going from 0 to 30. So that's what I'm going to make my x scale be. My y scale, the biggest y is on this is 6.6887. So I'm just going to put 7 for my max and 0 for my min. And this goes 1. Then I will go ahead and graph this and see what I get. I can see that I'm getting that nice down swooping exponential function that I drew earlier. And then I'm going to be getting this line. So now that I've got this downward swooping exponential function and my nice straight line, I'm simply going to ask it to compute where they intersect. It'll ask me which my first curve, what's my second curve. It'll ask for a guess. And I find out that this ends up happening when x on the calculator, but of course it's actually t. It's when t equals 12.633 day. So this is the 12th and a half day approximately. On the 12th and a half day out of the 30 days is when it first reached, when it actually hit the average amount. It also makes sense that this is before the 15th day because we talked about your decreasing faster at first. So all of this ends up making sense. And that is the answer to part C. Okay, so the last part of the problem is actually really simple, but there's something about the language of the way they write the last problem that will often get students and find them very confused. So I'm going to read exactly what it reads. For t greater than 30, so apparently we're after the 30th day in which we were modeled by this function, L of t, the linear approximation to a at t equals 30, is a better model for the amount of grass clippings in the bin. Use L of t to predict the time at which there will be exactly 0.5 pounds of grass clippings remaining in the bin. Show the work that leads to your answer. So let me just draw this picture and kind of show what's actually happening here. So I believe what we realized from before is that we've got this sort of down swooping. Here it starts out at 6.687 pounds. And it's this nice downward swooping exponential function that kind of looks like this. Here we are on day 30. And I think we found out that the amount was something like 0.9 something, 0.94 something. I could be wrong about that. I forget exactly what. It then says, after this point, instead of following this exponential curve, which is going to continue to level off forever and ever and ever, approaching 0, but never actually hitting it. At this point, what ends up happening is it now sort of decides to follow the tangent line to this curve at this point. So there's some tangent line right here. And that's what it ends up now following forever and ever and ever. And so according to this tangent line, there is going to be a place, for example, where it actually, we decompose all of the clippings. They're not asking for when that is, but if we were to continue following this function would say there is never such a time. We just get closer and closer to having 0 grass clippings. But since we suddenly jump and switch to this model, this new linear model, that's what's going to end up happening. So what do we need to do? Our goal in this problem is to figure out, okay, so when is it at 0.5? 0.5 is like right there or something, 0.5, and we want to know at what time do we end up hitting 0.5? All right, so our first goal then is to find this linear function. But that shouldn't be too hard. It's just the tangent line, right? So what do we need to compute this linear function? They call it L of t, by the way. We're only looking at L of t when t is greater than 30. But what does the local linear approximation equal? So it's a line. So this is the y value of your line. So it's y L of t minus the y value at this point. So we figured that that was a whatever a of 30 was. I believe we said that it was like 0.9 something or other equals a prime of 30 times, usually I want to write x, but it's t minus 30. So in other words, L of t equals a prime of 30 times t minus 30 plus a of 30. And we simply need to set this equal to 0.5 and solve for when these two things are equal. Okay, cool. So that's exactly what I'm going to do. And I'm even going to do it, I'm going to use a grapher and do it again with the grapher. So that's how I'll figure this one out. So I'm going to put in y3. I'm actually going to put this local linear approximation. So let's see. That ends up being the derivative. That ends up being the derivative with respect to x of y1 at 30 times x minus 30 plus y1 of 30. Okay, and then the other thing I'm going to put in for y4, I'm going to put in 0.5. I'm then going to turn off y1 and y2 because I don't need to see them. And I'm also going to go in and change my window again. My window now, our x-min now is in fact 30. And I don't know, we'll go up to like 60 or something. Our y max now is like 0.5. Or I'm trying to figure out when it equals 0.5. So I'm going to put my y max as 1 and my y min is 0. And I'm going to graph them and see what I get. So a nice line is being built here. There's 0.5. And then we're second calc, intersect. First curve, second curve. Yes. And it finds out that this happens when x, or in this case, t, equals 37.274 day. I would probably write this as, this happens on the 37.274